So next thing we need is the exponential distribution. We've been talking about continuous distributions. We talked about the uniform and the normal. So we have two famous continuous distributions. We've already done all the discrete distributions we need for the entire semester, but we only have two continuous distributions, so we kind of have to catch up on the continuous stuff. Okay? So the next most important one is called the exponential distribution, and that's one of the biggest topics for the next homework, and it's one of the most important distributions in general. Now, we've already seen the exponential distribution a couple times as just like, as part of like on the previous homework with waiting for the book to be released, and I used it to illustrate universality of the uniform. But we haven't formally introduced it yet. So this will be our formal introduction of the exponential distribution. So stat 110, this is the exponential distribution. Exponential distribution, this is stat 110. Now you're friends with the exponential distribution. It has one parameter, lambda, usually called lambda, but you could call it whatever you want. That's the traditional. And I'm going to call this a rate parameter, because you don't have to call it lambda. It's just lambda is the usual terminology. I'm going to call it a rate parameter. Because intuitively we can think of it as the rate at which some type of event occurs. Okay? So let's just write down the PDF and the CDF and so on, and then we can start to see why is this important compared with, of course, there's infinitely many PDFs we could write down, but what's special about this one? Okay, so we say x is exponential lambda. That's our notation, and it has a PDF that's given by lambda e to the minus lambda x for x positive and 0 otherwise. So it's always positive. It's a continuous positive random variable. That's the PDF. You can see why it's called the exponential distribution, because it's just an exponential function with a couple constants stuck in there. Exponential decay. This is a valid PDF, because if we integrate lambda e to the minus lambda x dx from 0 to infinity, that's a very easy integral, and we get 1 just integrating the exponential. So that means it's valid. Okay, let's get the CDF, and then let's figure out the mean and the variance, stuff like that, and then we can talk more about what are the special properties of this distribution. So let's get the CDF. Since we have the PDF, it's easy to get the CDF just by integrating. So f of x equals the integral. So I'll start the integral at 0 because this is a positive random variable. 0 up to x of lambda e to the minus lambda t dt. Again, that's a very easy integral, and you'll just get 1 minus e to the minus lambda x for x greater than 0. It's easy to check that this is correct, because if you take the derivative of this, lambda comes down and you get this. And also notice that this is a CDF, because just check that this is an increasing function, right? And as you let x go to infinity, then this part's gone and it goes to 1. And if you let x go to, well, you can't let x go to minus infinity, but if you let x go to 0, then you get 0, and then it just stays 0 if you go that way, right? And it approaches 1 if you go that way. Okay, so that's a valid CDF. It's continuous as well. Okay, well that's easy enough. Let's get the mean and the variance. Actually, an easier way to get the mean, but of course we can just write down the integral and do it. But before we do that, it's useful to try to standardize it. So remember, with the normal, we can reduce any normal to a standard normal. In this case, the normal has two parameters, mu and sigma squared. Here there's only one parameter, lambda. Okay, and we're going to show right now that if we let y equal lambda times x, then we're going to show that y is exponential of 1. So that's kind of analogous to standardization of the standard normal. in that we're multiplying. I mean, it's not exactly the same because for the normal we subtracted the mean divided by standard deviation. Here we're just saying multiply by something to make it exponential of 1. Because if I can get exponential of 1, it's going to be a lot easier, right, than the lambdas are not there. So how do we do that? So let's just do a quick calculation to show that that's true. Okay? Because once we have this relationship, then a lot of the times we can just work with exponential of 1 and then stick in the lambda, when we need it. So let's just compute the CDF of y. Y less than or equal to little y. Right? This is a very easy calculation if you understand CDFs. That's the CDF of y, but y is lambda x, so that's x less than or equal to y over lambda. But that's just the same as the CDF of x evaluated at y over lambda. So if we take this CDF and plug in y over lambda, then we just get 1 minus e to the minus lambda, right? X. Well, that's y there. That's the CDF of an exponential of 1, right? I just plugged in y over lambda here, and lambdas cancel, okay? So it's just that one short equation proves that this statement is true. Okay, so let's first concentrate on the case where it has parameter 1 and find the mean and variance, and then we can get the general case. Okay? So let's do that case now. So we're letting y be exponential of 1, and we want to find the mean and variance. Okay? So let's get the mean first. Just by definition, expected value y is just the integral of y times the PDF, e to the minus y dy. Right? Okay, now this is a very standard integration by parts. This is the kind of integral that you would see in AP calculus when you're learning integration by parts, right? So all we have to do is let u equal y and let dv equal this part. Remember your integration by parts, uv minus the integral of v du. So that's u, du equals dy, and v equals, just integrate this thing, right? So minus e to the minus y. Okay, so now I'm just going to do uv minus the integral of v du. So it's minus y e to the minus y, evaluated from 0 to infinity, minus a negative. So it's going to be plus the integral of e to the minus y dy. So now we made it into an easy integral. This first part is 0, because if we plug in y equals 0, we just get 0. If we let y go to infinity, well, this y is going to infinity, but e to the minus y is going to 0 exponentially fast. And this part's only growing linearly, so the exponential part's dominant. So this part is just 0. And this part is just 1, either because that's an easy integral, or an even cuter way to do it is to say, well, we're integrating the exponential 1 PDF. It has to be 1, otherwise that wasn't a valid PDF. So in this course, there are actually a lot of integrals we can do, not using calculus, but by recognizing, oh, that's a PDF, or that kind of thing. Of course, that's an easy integral anyway. Okay, therefore the mean is 1. Now, for the variance, we can just do e of y squared minus e of y squared the other way, as usual. So here's just a lotus, e of y squared. Well, we just by lotus, it's immediate that that's the integral of y squared e to the minus y dy minus this thing we just computed as 1. Okay? Now this integral, well, then we have to use integration by parts again. And I'm not going to write out the integration by parts again, partly because we're going to learn better ways to do this later, or we're going to actually avoid doing this and get the moments a different way. Well, this is called the second moment, by the way. E of y is called the first moment. That's called the second moment. Okay, but this is an easy integration by parts in the sense that if you let u equal y squared, basically it's going to reduce it back down to an integral that looks like this, right? It's going to lower the power from 2 to 1. So this is like one where you do integration by parts twice. You don't actually have to do it twice, because you do it once, and then you reduce it to the one we just did. So you actually do integration by parts once. And if you do that, you also get 1. And that's pretty easy to remember. Okay? So now coming back to this general exponential. So just continuing the notation here. Y equals lambda x, so x equals y over lambda. And that's going to have the mean. Just take the expected value of this. Lambda is a constant. That comes out. So it has mean 1 over lambda. And it has variance. Well, for the variance, take the variance of this. Remember, the variance constant come out squared. So it's 1 over lambda squared times the variance of y, but the variance of y is 1. So the variance is 1 over lambda squared. Okay, so now we know the mean and the variance. We do not yet know why the exponential is important, okay? And there's different reasons why it's important, but what I consider the most important reason is what's called the memoryless property. And you've already seen the memoryless property in the discrete case if you did that practice midterm question, but we haven't talked about it in the continuous case. So memoryless property. Okay, so exponential distribution is memoryless. I have to tell you what that means and then check that it's true. Okay, so memoryless property means that, well, see if we can remember. See if we can remember that midterm practice problem. What did it said something about memorylessness. It said no matter how long you've waited, then it's like you're starting over from fresh. Okay, I think that's what it said, right? So it says that if you have a random variable that intuitively it's a random variable that we interpret as a waiting time. So you're waiting for something to happen, right? So just to have a concrete example in mind, suppose you're just waiting for a phone call, right? So now is time 0, okay, and you're waiting to get a call. Okay, which could come at any time in continuous time, right? The geometric is discrete, like flipping coins, waiting for success, right? Bernoulli trials wait for success in discrete times because you have discrete trials. This is in continuous time. You're waiting for the phone call, and suppose that this waiting time has the property that no matter how long you waited, just like that time is gone, it's not giving you progress towards getting your phone call. It's like starting from fresh every time, okay? That's what the memoryless property means. So as an equation, what it says is the probability that x is greater than or equal to s plus t, given that x is greater than or equal to s. That means you've already, imagine that s is measured in minutes or whatever unit you want. This says you've already waited at least s minutes. You've already waited s minutes. And you haven't gotten your phone call, so you know x is greater than or equal to s, okay? And then what's the probability that you would have to wait at least an additional t minutes is just the same as the probability that x is greater than or equal to t, because you've started over with a fresh exponential distribution with the same parameter. That's the definition of the memoryless property, but I hope that this equation kind of intuitively makes sense to capture that intuition of memorylessness. Okay, so now let's prove that in fact that this equation is satisfied by the exponential. So for the exponential lambda, this is the general definition, but now we're assuming x is exponential lambda, and let's check that equation holds. So we need to find, let's find the probability that x is greater than or equal to s. That's 1 minus the CDF. So we don't have to worry about whether it's strict inequality here because it's a continuous random variable. So this is just 1 minus the CDF. And this is sometimes called the survival. This is called the survival function because it's, what's the probability that if you think of x, rather than thinking of a waiting time, thinking of it as like how long someone's going to live. And then that's the probability that they would live more than at least s seconds. So that's a survival thing. So this is actually extremely important in what's called survival analysis, in biostatistics, as well as in engineering. You know, you want to figure out how long is this, you know, a certain piece of electronics going to last, things like that. Then you need to look at survival functions. Well, anyway, that's just 1 minus the CDF. But the CDF was 1 minus e to the minus lambda x, so that's just e to the minus lambda s. So it's a very easy-looking survival function. So now, the probability that x is greater than or equal to s plus t, given that x is greater than or equal to s, let's just use the definition of conditional probability. So this is the probability that x is greater than or equal to s plus t and x is greater than or equal to s divided by the probability that x is greater than or equal to s. Just definition of conditional probability. But notice that the numerator is slightly redundant, because if we say it's greater than or equal to s plus t, I'm assuming s and t are non-negative real numbers. If it's at least s plus t, obviously it's at least s. So this part is redundant. So it's, in other words, it's just the ratio of the survival function here over the survival function here. So we just compare, and this is true for, you know, for all s greater than or equal to 0. So that's just e to the minus lambda s plus t divided by e to the minus lambda s, and that just simplifies to e to the minus lambda t, which is the probability that x is greater than or equal to t. So that shows that it's memoryless. Now, you might imagine that there's millions of other memoryless distributions. But it turns out that the exponential is the only one. This completely characterizes it. And just one more quick, we'll prove that next time, but one more quick restatement of the memoryless, or consequence of memoryless property. Here's a corollary of this memoryless property that's often useful. Again, we're letting x be exponential lambda. And suppose we want to know the expected value of x given that x is greater than some number a. This is our first time actually using this notation, conditional expectation, but you should already know what this means, right? Because this just says take the expectation, but instead of using probability, use conditional probability. So it's defined in the same way, except use conditional probability. That gives us conditional expectation. So intuitively, it's just like, given the information that you've waited at least a minutes for, what's the probability, you know, what's the expected value of x given that information? Well, we could think of that as a plus e of x minus a, just linearity, pull out an a. The cool thing about the memoryless property is, given that x is greater than a, this thing x minus a just becomes a fresh exponential, right? Because this is the additional waiting time. You waited a, but it started over again, right? So it's immediate that this is just a plus 1 over lambda by the memoryless property. Otherwise, you'd have to do some calculus, do integration and stuff, but we can avoid that but just by in this case, and in some other interesting problems, just by using this property.